So hi and hello, welcome to our channel named Algo Exploration. My name is Samir and today we will be going to continue the finding of time complexity from the recurrence relation. In the previous video I have shown you using the substitution method, but today we will use the recursive tree method. Now let's understand by taking one example. Here t of n is equals to 2t n by 2 plus n. Now t of n is calling t of n by 2 twice. And what about n? Please observe here, t of n is calling t of n by 2 twice. Now when t of n by 2 is returning the value to its parent, that is t of n, the cost for combining these two results from n by 2 and from n by 2 is nothing but n. So I hope you got what actually n is. Now let's go further. Now t of n is calling t of n by 2 now the cost at this level is n, that is combining the return value from this and this. Similarly n by 2 will also call t of n by 2 square. Why 2 square? Sorry, why n by 2 square? Because in place of n we are putting n by 2. Similarly here also t of n by 2 square, and here t of n by 2 square. Now the cost of this will be n by 2. Similarly the cost will be n by 2. Now the cost at this level will be 2 times of n by 2. So it will be n only. Now similarly this function will also call t of n by 2 cube, and again here also t of n by 2 cube. Similarly this function also called, and this function also called t of n by 2 cube 2 times. So the cost here will be n by 2 square, here also n by 2 square, n by 2 square, and n by 2 square. So the cost at this level will be 4 times of n by 2 square. So it will be n. So we can see that at every level the cost is n only, but sometimes the cost of every level will be different. Here in this case it is coming out to be n. Now if we do this for k number of times, this will be t of n by 2 raised to k. Similarly here also, because it is turned out to be a balanced tree, t of n by 2 raised to k. Now to make this as 1, n by 2 raised to k equals to 1, we found out value of k is equals to log n. Now what actually log n means? It is nothing but the height of this tree, because at every level it is dividing by 2. So the height of this tree is log n, and at every level the cost is n. So the time complexity for this recurrence relation is log n height of the tree, and at every level the cost is n. So order of n log n. So just for revision, let's find out using the substitution method whether we get time complexity as order of n log n or not. So T of n is equals to 2T of n by 2 plus n. So T of n by 2 is equals to 2T of n by 2 square plus n by 2. T of n by 2 square is equals to 2T of n by 2 raised to 3 plus n by 2 square. Now this is substitution method. I suggest you please watch the previous lecture. So this will be equation 1, 2 and 3. Now substituting this value in this part, we get T of n by 2 into 2 of T n by 2 cube plus n by 2 square plus n by 2. So if we open the bracket, we get 2 square T of n by 2 cube plus n by 2 plus n by 2. Now we got the value of T of n by 2, so we will put in this. So we get T of n is equals to 2 into 2 square T of n by 2 cube plus n by 2 plus n by 2 plus n. So this will be 2 cube T of n by 2 cube plus n plus n plus n. Now if we do this for k number of times, this will be 2 raised to k T of n by 2 raised to k plus k into n. We can see that this n is nothing but 3n. Now to eliminate this T of n by 2 raised to k, we have to put n by 2 raised to k equals to 1 because of base condition. So the value of k will be log n. Now we have to put the value of k in this equation. So 2 raised to log n, the base is 2 here, into 1 because this is 1 plus log n into n. Now the value of this is n plus n log n. The dominant term is n log n, so we get that order of n log n, which is same. So in the next lecture, I'll show you how to use the master theorem to find the time complexity. The master theorem will be the shortcut to find the time complexity of the recursive code. So thank you.